Hello, welcome back to Proximity Math. I'm going to go over the 2010 Aime Ii number 11. Define a T-grid to be a 3x3 matrix satisfying these properties. This is a 3x3 matrix. Exactly 5 of the entries are 1s, so we have exactly 5 1s, and the rest 4 are 0s. Among the 8 rows, columns, and diagonals, so the rows, columns, and diagonals, no more than 1 has all 3 entries equal. So let that sink in. No more than one of these has all 3 entries equal. This means if we want, we don't have 3 in a row, like here for example, we don't have 3 in a row more than once. And this can be in a diagonal too. Okay. So the way to have no more than one of these, we can have 0 cases where there's 3 in a row, or 1 instance where there's 3 in a row. For the 0 case, you can count these kind of easily, but if you want to find the ways for there to be no 3 in a row, you're gonna find it's actually pretty hard, and there's no methods that obvious. At least there's no method that's obvious right away to count the ways to have no 3 in a row. Alright, now if you want, the only other way to go is complementary counting. So first we find the ways to have 5, 4. We're gonna find the ways where the first condition is true, but the second is violated. So we have 5 1s or 4 zeros, and you can do a 9 choose 4 to find the ways to place them, which is 126. Alright, now 126 minus something, the number of cases violating the second condition, is the answer. So we want the cases where there's more than there's more than one of 3 1s in a row, or 3 1s and there's 3 zeros in a row. So we want 3 1s in a row twice, or we want 3 1s and 3 zeros. These both violate it. No, we cannot have we cannot have 3 cases of 3 1s in a row in any way, or same as zeros. Obviously, there's less zeros, and we cannot have a case where there's 3 zeros in a row and it violates the second condition, because this case, what this means is there's 3 zeros in a row twice. That means we don't care about the ones yet. We want 3 zeros in a row twice, and there's no way to do that with only 4 zeros. So I'm excluding that case completely. Okay, if we have 3 1s in a row twice, that's what this case means. Violating the second condition, there's 6 ways to choose the row or column to put the 1s in, and then we have 5 1s, so we can't choose a separate row to put them in. We have 5 1s, so we can put them like this or like this. These are easy to see. So there's 3 ways to do this depending on what row or column you choose. Actually, not depending, it's independent of which row or column you choose. You'll always have 3 ways to place these. Okay. And then we'll have, also be very careful when we have this case. For example, let's say we choose 3 1s in a row, then we add these 2 later. What if we chose these 3 and then added these 2 later? Because it's symmetric, we have to divide by 2 to not overcount. Okay, now that we have that aside, and we have one more case where we can do something clever with the ones. What if you have them in diagonals, 2 diagonals like this? So we have 2 cases where there's 3 in a row, and there's only one way to do this. Okay. Now the case, you have 3 ones in a row and 3 zeros in a row. Okay. There's 6 ways to put the 3 ones, first of all. If you put 3 ones in a diagonal or 3 zeros in a diagonal, there's no way to put the other number 3 in a row. You should notice that. Like, if you have 3 ones in a diagonal, there's no way to put the 3 zeros in a row either. Okay, so there's 6 ways to choose the row or column for ones. And then we need 2 more ones and the rest are zeros, so that we have 3 zeros in a row. You can only have 3 zeros in a row if they're one of the parallel columns or rows to this. And the only way to have 3 zeros in a row if you have the other 2 ones in the same row or column. So if you have this, it's not possible. We must have this or something like this or this. So if you have 3 zeros in a row, there's two places we can put these, and then 3 choose 2 ways to put the zeros. So 3 choose 2 ways to put the remaining 2 ones. Okay. So that gives us 36 ways. All right. Let me look back over here. All right, there's one way to put them in a diagonal like this, assuming we have 2 cases of 3 ones in a row. And then we can have something like this too. We have 6 ways to choose this, and then 3 ways to put these. Oh, I forgot. To form a diagonal, we can also do this. That's the last case. And there's 2 ways to do these. You can put the 1 here too. You can put this one over here. And this gives only 2 ways to do it for each of the 6 ways to put the 3 ones in a row. And there's no overcounting because we have a row and a diagonal. So you find out we get 58 from this. And you can be careful and check over it to make sure we miss no cases. It's kind of hard to do that, but this is an aim number 11, so of course it can be hard. And this gives us a final answer of 68. Alright, that was some tough case work. And the reason I did this method because I looked at the other solutions. There's no doable method. Like, there's no manageable method, at least for me. So this is my own method, which seems to be relatively simple. Alright, thanks for watching, and I hope this helped you.